Welcome back to the next section of Chapter 11. In this section, we're going to be looking at independent and dependent events and how to deal with those probabilities. Independent and dependent events are ways we can combine the probabilities without having to figure out the total number of successes and the total number of total possibilities. We can use the probabilities and multiply them. A lot of you have actually been doing this in the past sections, so I have a feeling that some of this is definitely going to be a review. One of the things that we'll see from this section is we're going to use the word "and" a lot. We're going to have event A and event B. The next section will use the word "or," but these are a lot of "and" situations. So our learning targets today: I can determine whether events are independent or dependent, and then I can find the probability of independent and dependent events. So let's look at what these independent events and dependent events are. An independent event is where the outcome of one event does not affect the outcome of future events. For instance, when we're flipping a coin, you can flip a coin 20 times. The next coin flip is going to be 50-50, heads or tails. And that's actually a good thing. Otherwise, you'd have to know the entire history of a coin in order to determine the probability of the next flip. But it's always 1/2 for heads, 1/2 for tails. And that's something that gets people. If you flip a coin 20 times and you get heads 20 times in a row, what's the probability of getting heads on the next flip? And people a lot of times will think, well, it's got to be tails. Tails has to be coming up. No, the probability is still 1/2. In fact, if I got heads 20 times in a row, I'd start thinking that it's not actually a fair or even coin, and I'd start thinking it was probably going to be heads a lot more often. But in a fair coin, which means it's 50-50, 1/2 and 1/2 each time, it doesn't matter what the previous flips were. The next flip is always a probability of 1/2. In the same respect, dice rolls. Every time you roll the dice, you have 1/6 of a chance of getting each of the 6 numbers. Or if you're using different size and shape dice, 1 out of however many sides you have on that dice. And if you're picking things with replacement, if we have a bag of marbles, we pick out a marble, we look at it, and we put it back, and then we pick another marble. That is independent because the first pick did not change the probability of the second pick because we put it back. If we didn't put it back, that becomes a dependent event, and we'll talk about that in a few minutes. So we have an equation for independent events. And that would be the probability of A and B, two things happening, is just the probability of A times the probability of B. If they're independent, we can just multiply the probabilities together to get the probability of two things happening. Or if we have 3 things, 4 things, 5 things, as long as they're all independent, we can just multiply the probabilities together. It expands perfectly. So let's do some examples. Let's say we roll 2 dice and we're going to get 2 4s. So the probability of a 4 and a 4 would be the probability of getting a 4 times the probability of getting a 4. What's the probability of getting a 4? 1/6. So it'll be 1/6 times 1/6, which is 1/36. Now this works when we have 2 4s. If we had a 3 and a 4, that could be different because we could get a 3 on the first one, then a 4 on the second, or a 4 on the first one, a 3 on the second. And so when things are different, it does get a little bit more complicated, but that's not one of the things that we're going to be looking at today. That'll come up next week. Another example, flipping 4 coins and getting 4 tails. So here we have more than 2 things happening. Well, that's okay. The probability of getting 4 tails is just the probability of getting a tail times the probability of getting a tail times the probability of getting a tail times the probability of getting a tail. Each of those is going to be 1/2. So we just multiply all those together to get 1/16. And so that's independent. Earlier, we were looking at like doing this type of problem with the dice. It's like, all right, well, how many ways could we get 4 on the first dice? 1 times how many ways could we get 4 on the second dice? 1 over how many ways could we roll the first dice? 6. How many ways could we roll the second dice? 6. And we do it as one big fraction to begin with. Now we can do each probability separately and then just multiply them. And that's what you guys have been doing already. Dependent events are outcomes where one event does affect the outcome of future events. So I'd already mentioned picking things without replacement. If I have a bag of marbles and I pick a marble out of the bag, the probability of the bag has changed because there is one less marble in it. Decks of cards will also is typically without replacement because you don't get a card, look at it, and put it back. You get a couple cards. Each time you get a card, that's going to change the probability of the deck. And also, sometimes we know more info about an event. For instance, if we wanted to pick someone out of the class who was both a guy and a sophomore, that's knowing more than one thing about that one event that can change the probability. And we'll see that in just a minute. But first, let's look at the equation. The equation is going to be very similar to the independent equation, except we have this funny thing. So the probability of A and B is the probability of A times the probability of B with a slash and then an A. And what that is it's called a conditional probability. This is the probability of B given that A has already happened. So that's where you change the probability of the deck, the probability of the bag of cards, things like that. So we know that A has happened. Now what's the probability of event B happening? And so let's look at this. And this is actually a lot easier than the equation makes it look, because this is kind of scary. You see it, and it's like, I don't even know what's going on there. But you would probably, in fact, I'd say you would probably already do it. We have been doing this already. We just haven't called it a conditional probability. So let's draw 2 cards and get 2 aces. So that's going to be the probability of an ace and an ace. So that's going to be the probability of drawing 1 ace times the probability of drawing an ace, given that we already have one in our hand. So for the first one, what's the probability of drawing an ace? How many aces are in a deck of cards? 4. Divided by how many cards are in the deck of cards? 52. So that first ace is 4 over 52. Now if we have an ace in the hand, how many aces are left in the deck to draw? 3 out of how many cards? 51. That is the conditional probability. It's just we already have 1 card. Well, now there's only 3 out of 51 cards left. And we can multiply that together to get 1 over 221. This also extends just as well as the independent ones extend. The equation gets a little bit complicated. The next one would be probability of C given A and B, and then would be probability of D given A and B and C. So basically, given that everything else that came before this already happened, what's the new probability? In actual practical problems, it works out a lot easier. Example, let's say we don't want just 2 aces. Let's say we draw 4 cards. We want all 4 aces. And so that's going to be the probability of the first one, which is going to be 4 over 52, and then 3 over 51. And then what would the next probability be? 2 over 50, and then 1 over 49. And we just need to multiply those together and simplify to get 1 over 270,725. Obviously, it's very difficult to get 4 aces out of 4 cards. Um, and so that's dependent events. And we've been doing this with our permutations and stuff. We've been finding these numbers. This just splits the fraction up into 2 different pieces or 4 different pieces, and then we just multiply them together. But it's basically the same. So let's look at knowing more information about one event. See what type of thing that looks like. So here we have a problem from the book. The table shows the result of a quality control study in a light bulb factory. It's a bright study. A light bulb from the factory is selected at random. Find each probability. And so we have some information. This is called a two-way table, by the way. We have some defective light bulbs. Some were shipped, 10 of them, and 45 of them weren't shipped. And we have not defective light bulbs. 942 of them were shipped, and 3 of them were not shipped. And then we have the shipped and not shipped, which goes with the defective and not defective as well. And so we want to find the probability that a shipped bulb is not defective. So we know that it is shipped. We're going to look for the probability that it is not defective given that it is already shipped. This first one is usually a given. Because we have a shipped bulb, we want that to be not defective. So in this problem, this not shipped, that doesn't even matter. This is going to be the whole universe of this conditional probability. So we know it's shipped. What's the probability it's not defective? How many not defective bulbs do we have? 942. Over how many total shipped bulbs do we have? Add these together, 952. And you could reduce that. We can also look for the probability that the bulb is defective and shipped. So for this one, we need the full deal because we don't have anything given. We just want to know what is the probability that's defective and shipped. Now, and this is going to bring us to the question of, is it independent or not? For this, we actually don't need to know whether or not it's independent. We'll check that in just a minute. How many bulbs are both defective and shipped? Looking at the table, defective, shipped, we have 10 bulbs that are both defective and shipped. Divided by how many total bulbs did we have? If you add these guys up, you get 1,000. So we have 10 over 1,000, which is 1 over 100, which is 0.01 if you are into the whole decimal thing. And so how can we tell from this if these two things are independent? Because sometimes the independence makes sense. You can think about, well, did what I just did affect what I'm going to do? And that answer could be clear, either yes or no. But sometimes, like we're looking at this, it's like, I don't know. I think there's a relationship there, but I'm not entirely sure if it's independent. Well, to tell if it's independent, we can actually look at the equation. If they're independent, then the probability of A and B will equal the probability of A times the probability of B. That equation that we had for independent events is actually the definition of independent events. If that is true, they are independent. If they're independent, that is true. So if we have these 3 numbers, we can check to see if they're independent. And I know that's something that people tend to miss on the test because they always just resort to, well, it doesn't seem like they'll make a difference. Well, maybe they do. Actually check it using the formula. And so defective and shipped, that's this number, the 10 over 1,000, 1 over 100. What's the probability that they're defective? Well, how many defective bulbs did we have? 10 and 45, that's 55 defective bulbs. So we have 55 over 1,000. How many shipped bulbs did we have? 952 over 1,000. And so we're just checking to see, are these two things equal or not? So we can multiply these guys and divide. I'm going to make it a decimal because sometimes decimals are easier to compare. This can be a decimal as well. That's 0.01. And we multiply and divide these, we get about 0.052. Are these two things the same? No, they're not the same. 0.01 is not the same as 0.05. Now, if it was really, really close, could it be the same? Yeah, maybe. It's not going to be really, really close, though. It'll either be independent or it won't be independent. Not going to try and trick you. And so, since these are not the same, the probability of the two things multiplied together does not equal the probability of both of them, which we can find from the table, then no, they're not independent. And so this is what we're doing today, tomorrow. We are finding independent probabilities, finding dependent probabilities, and then testing to see, are they independent or not? Using a table, using dice, which a table of dice where you have 1 through 6 and 1 through 6, so you can see all the possibilities. That helps for some of those questions. And there's actually a really good one, just if you flip back a couple pages in the book, there's a great one, but you can also make them pretty easily too. There's only 36 possibilities. Anyway, enjoy the rest of your evening, and I will see you in class.